Welcome back to Tezos Explained. We're delighted again to be joined by Tezos co-founder Arthur Brightman, and we're going to jump into a slightly more technical topic today, RISC-V. A number of people might be wondering, what is RISC-V? On the Tezos X roadmap, you can see coming the RISC-V engine, the runtime for Tezos X. So what do you mean by like the runtime for Tezos X?
Yeah, so you can think of the way Rollup works as a form of verifiable computation. You don't want every validator in the whole set to like do the whole computation. You need to be able to verify the computation, and you want to be able to verify it tuply. So one way to do that is Validity Rollup. You'll verify it by producing a cryptographic proof, and then everyone sees the proof and they verify it. The downside to that is that creating that proof is very, very expensive. It's 3 orders of magnitude more expensive than like running the actual code. It might come down in the future, but for now, this is where we are. In an optimistic rollup, the way you do it is you're going to allow people to challenge a commitment. But in order for these challenges to happen, in order to even have a discussion as to like what is correct execution, we need to have a very, very precise definition of how anything is executed. And in the case of an optimistic rollup, you don't just care about the final outcome, you care about the whole process of how this thing was executed. So for that, we need a virtual machine. And I think a lot of people who are a little bit technically interested into blockchains will know about that, because we have these virtual machines for writing smart contracts. But here we want a more generic one, because we don't want to just write simple smart contracts. We want to write bigger code. We want to write compile code. So we need a really generic backend to compile this. So far we have optimistic rollups on Tezos, but we've used WebAssembly, WASM, as the virtual machine and as a backend. And instead now we want to be using RISC-V. Why are we not using WASM? Why are we using RISC-V now?
Yeah, so 2.5 years ago, when we were sort of starting to build the first generation of rollups on Tezos, we did go with WebAssembly. And both RISC-V and WebAssembly, I think you could describe as sort of emerging technologies. They were sort of, to a certain extent, like well understood, but tooling was there for sort of to different levels. Mm-hmm. So one of the reasons that actually we went with WebAssembly to start off with is it was in a way the safe bet. It was what the rest of the industry was looking at. So Arbitrum, for example, was looking at WebAssembly for running the sort of verification as well. And so to be able to say that actually we're using what the rest of the industry is using, there was one part of it that we weren't worried about necessarily whether or not it would be a success. It was a technology that at the time was starting to have support from a number of different tools. So for example, Rust had relatively recently got WebAssembly support, but actually in a really, really nice manner. So a lot of the stuff that you wanted to do, that you would do with like a normal Rust program, you could do with WebAssembly sort of out of the box. But there are also then 2 different flavors of WebAssembly. And this is where WebAssembly started to show a few cracks, at least for our use case. Mm-hmm. So a lot of tooling out there assumes that you have a sort of Unix-like API available. Yeah, that there's some sort of host operating system that you can talk to. In WebAssembly, this is done through the WASI interface, which is this huge interface full of functions that you can use to contact the external world.
But there's an advantage for WebAssembly.
It is. At least when you use like WASI, you have a lot of tooling available to you, and there's not as much work to do to get tooling, for example, like SQLite. There's a tool that like, a lot of programmers use, and you can get that working on WebAssembly with the WASI backend. But unfortunately, because the sort of specification that WASI requires is massive, that actually means that for us, we decided not to implement anything like that and instead of roll our own, which meant that the actual like surface between what was happening sort of computation-wise and then what was happening under the hood in terms of the way that we could communicate with the external world was very limited, and we could control that very well. But that does mean that a lot of tooling that assumed the existence of WASI wasn't available to us ultimately with WebAssembly. And that's 1.5 of it. And we'll get into a little bit how RISC-V enables us to pull in bits of ecosystem and tooling that we didn't really have access to with WebAssembly. The actual other part of it is much more sort of technological and tied to WebAssembly itself. And that is WebAssembly by design is like very, very static. It's a low-level language, but it is still relatively high level. It's got many sort of instructions and pieces which are themselves like high level and belong to like a high level programming language. These restrictions mean that one thing that a lot of programs love to be able to do that you can't do in WebAssembly is create code at runtime and run it.
Yeah, and that's important for JavaScript, for example.
Exactly. I mean, there are obviously many different JavaScript interpreters out there, which are performant to different extents. But if you tie yourselves to interpreted JavaScript only, the overhead of the language really makes itself known. And if you want computation or the throughput of the system to be so high that you don't have to worry about, for example, fees ever like going up, restricting ourselves to non-performant technologies doesn't really make sense.
Yeah.
So RISC-V comes with a lot of benefits. It is extremely low level. It is ultimately the instructions that a CPU would execute, very much like x86 or ARM. But it is also very simple. And this gives us two real benefits. The first is that we can actually be very, very confident about what executing a RISC-V instruction means in terms of like the runtime and the space complexity of that instruction. And this is really important when it comes to the proof verification. And the other part of it, because it's so level, it is very easy to create new code at runtime and compile it. Like any other just-in-time compiler that works for x86 or for ARM can be made relatively easily to work for RISC-V.
So on that note, back on the industry adoption, I see more industry adoption now of RISC-V, so we're not the only ones, turning towards RISC-V after looking at WASM. But, if the goal is to basically take what's most standard, why actually not just do x86?
So everything compiles for x86, everything runs for x86. So we would have the whole world available to us out of the box. Again, the issue comes down to time. x86 is a huge instruction set. It has a lot of historical complexity, a lot of historical tech debt as a result of Intel and AMD wanting to make sure quite correctly that programs that compiled for old processors still work for the new ones. But because it's such a big instruction set, there are so many things to do, it would actually mean for us that it would take far, far longer to create a system to run that.
What about taking an old 86, like 8086, or like some of the original 86 instruction sets?
You can do that as well, but again, you're starting to limit yourself to like older tooling, older compilers, and some of the state of the art, for example, like newer Rust versions, newer C++ versions, they don't always work for those old processors anymore. And indeed, even if the compilers themselves work, some of the tooling doesn't anymore.
Yeah, okay, that makes sense.
The other side of RISC-V that becomes actually really, really nice is we're taking the view of, obviously, there were two big restrictions with WebAssembly. The first that we found, obviously, being the difficulty of getting like all the ecosystem or all the tooling that developers are used to available on WebAssembly. With RISC-V, we are deliberately avoiding that completely. So in the early sort of proof of concept work, we've been using a unikernel where we would compile the rollup program we want to run.
So that's what you were saying is like, WASI doesn't have to assume that you have a whole Unix environment. It could give you a lot of that, but RISC-V is very bare bones. Does it mean we have to run a whole like Unix kernel around it to use it?
Exactly. So in order to get something working as quickly as possible, we did take that approach. And we would bundle it with a sort of roughly Unix-like unikernel that would run directly in the virtual machine. But we are moving away from that. So we are very, very keen that there's anything that can run basically for Linux, RISC-V, should run for us as well.
I'm glad and sad at the same time. Sad because it's like the idea of like, well, we just run Unix. It's so cool. And everything that you can compile for Unix, you're just going to run directly. On the other hand, it's such a huge surface area. I'm not having to inherit all the potential security issues of a Unix kernel. Well, is a good saying.
So what we don't want to do is sort of bundle your program with Linux itself.
Yeah.
What we're doing instead is the program itself will still run at the user level, but we're actually implementing the supervisor in the virtual machine directly.
Yeah.
And there's a limit to how much we need to implement to do that sort of in a nice manner. So Linux obviously has a huge API surface. There are two ways we can restrict it. The first being actually we can look at only like the muzzle C library. So rather than looking at, say, like the APIs or the syscalls that glibc uses under the hood, we can use muzzle, which is already quite a lot restricted in terms of the APIs or the syscalls that it assume exist. And then we can also look at the programs that we actually want to run. And yes, there's a huge, huge history and there are so many possible syscalls out there. But actually, if you run strace over just the program that you want to use, there's a relatively limited API that we want to use. So we have, for example, the work in progress like Justice kernel. We ran strace over it and we found that actually there are only 13 syscalls when it runs natively on Linux that it actually uses.
Right. And so the program in this case is the JavaScript interpreter.
Yes, exactly.
But that might also depend on like what JavaScript program it's running.
So this is where the Justice team are also like working very hard because they want the API that's available for them to be as close as possible to the existing surface area that JavaScript developers are used to when like running a node. And there are two different parts to it. There are parts where they really have to call out to like a syscall to be able to do that, as like mmap, for example. Mm-hmm. But there are also many APIs that they can implement and have implemented themselves, which then use this very limited subset under the hood.
So when RISC-V?
Well, the RISC-V project's been in progress since sort of last quarter, last year, so end of 2023. We've made a lot of progress. So we've implemented a fully compliant RISC-V interpreter in Rust, and we passed the entirety of the test suite for the extensions that we care about.
But they are already RISC-V interpreters, so what do we need to write one?
Yeah, I mean, that's a really interesting question. So there's nothing out there that actually does what we needed for two reasons. Firstly, we needed something that was spec compliant with the RISC-V spec, and looking at a few different offerings out there written in Rust and also other languages, there are not really any RISC-V interpreters out there that are fully spec compliant. They take some shortcuts in some ways. Like we were using actually a Rust interpreter called RVEmu for quite a long time to sort of do our testing. And it works pretty well and it runs decently well, but it does take a lot of shortcuts with respect to like supervisor memory management and so on. The other part of it is by using it as our runtime, we have a lot of requirements for it that nobody else needs. We need to be able to run the computation, stop it at any point in time, be able to do the sort of proof generation and then verification for the refutability within the rollups as well. And taking a system, stopping it at any point in time, and then continuing whilst maintaining it and running it as fast as possible is a very unique requirement, and is actually something that we ran into a lot of issues with WebAssembly, is that we can have a virtual machine that can do this proof generation and verification. We have that, and it's embedded in the Tezos protocol, but you want to be able to run it quickly. And very often these two things are conflicting. There are state-of-the-art WebAssembly interpreters that run incredibly quickly. Wasmer is the one that we end up using within Tezos. And they run incredibly quickly and you can have an immense throughput in them. But they are completely opaque and you cannot stop them at arbitrary points and inspect the state. It's completely hidden from you because they want to do so many sort of optimizations under the hood.
So one change we have between like WASM and RISC-V, which I think is interesting, is gas counting. I've lived through that because I remember the Michelson interpreter for Tezos was really way before any gas monitoring, like gas counting for it was. And gas counting in the EVM was also the source of many bugs on Ethereum. It's a really hard thing to do. And when we did the WASM interpreter, I think at some time we discussed like, should your virtual machine count the gas for you? Should it do the counting, or is that the responsibility of the kernel developer? And for the first version of Smart Rollup in Mumbai, we went with the kernel developer. So the Etherlink kernel is responsible for monitoring its own gas and not exceeding the thing. And you will not have a secure rollup unless your kernel is careful about not exceeding a certain like gas limit. And it's responsibility to do that, and it needs to instrument itself and instrument whatever it executes to guarantee that. So we have some approximation. The benefit is that it lets you run Etherlink nodes in compile mode. You don't have to run them with a WASM interpreter. You can run them immediately. The downside is that it's a real hassle with the kernel development. And I think it was one of the biggest difficulty in Etherlink was doing that. So we're doing it different with RISC-V this time. We're doing the tick counting at the virtual machine level so that the kernel developers, whether it's for Tezos X or for like some application-specific rollup, don't have to think about it. It's just like a system call. It tells you like, how well are you doing on gas right now? The advantages are clear, but don't we lose performance in doing that?
There is obviously a little bit of an overhead to doing like tick counting. Now, this comes back as well to like, why not x86, for example? Now, the instructions in RISC-V are designed to be incredibly simple. So, for example, there's no way to copy like a series of bytes from memory to like another place in memory. You have to do it like byte by byte. And while this has a little bit of a performance overhead compared to, for example, like x86, the advantage is we can be very, very crisp with the step counting. We can say one instruction executed is one step. And that actually means that the overhead that we have for step counting is much lower, because we don't have to do any calculations to say, oh, it was this instruction, so actually it's like 10 steps because we were doing...
Maybe challenge that. Isn't that more steps? Because it means, now it's like if you want to copy a megabyte of memory, you're going to need to increment a gas counter like 1,000,000 times to...
So, like naively, yes, when you execute purely one by one, then yes, of course, like you are executing more instructions. There is a overhead compared to like compiling it and running it natively. So this is where one of the techniques that we are applying in the RISC-V interpreter is just-in-time compilation, not for like JavaScript in the kernel, but just-in-time compilation of the RISC-V code itself. Ultimately, the instructions are very simple, and we can clearly look at, for example, sequences of instructions and say, this is a loop, this is a small loop from copying like one place in memory to the other. And we can, ahead of time, say, okay, well, whenever we encountered this block of instructions, we've actually like natively compiled this function over here that will just do a memcopy, and we know the size of it already, so we just update the step counter by that amount.
Right.
The key is that we are still able to sort of stop at any point, because if we don't have enough steps remaining to execute the block in full, we fall back to what it was doing previously, which arguably is kind of the same as what we're doing with like Wasmer versus like the Wasm PVM in the protocol.
Yeah.
But on much lower and much more isolated level.
It's more emergent.
Much more clear. Exactly. Like from the outside, it always looks like you're running this RISC-V program for these many steps. And under the hood, we can take advantage of sort of much more smaller like optimizations.
All right. When are we going to get the first RISC-V rollups?
When are we going to get the first RISC-V rollups? So there's a little bit of a open question there, in all honesty. So one good candidate is Etherlink, and then another really good candidate is Justice. Yeah. So the Justice team are running in the existing infrastructure at the moment, but we have their kernel compiled to RISC-V. We're running it in the interpreter as part of our test suite. So they will be a really, really good candidate, and it depends on sort of when they're ready, and also when RISC-V becomes available on mainnet. Yeah. We're hoping to have it included in probably like 2 to 3 protocols time.
Yeah.
And at that point, it will become active on mainnet sort of 3 months after that.
So about a year.
About a year. But then Etherlink as well, we're like really keen to bring it over to RISC-V as soon as possible. But that then obviously has the overhead of like needing to migrate from Wasm to RISC-V, and that's something that we're actively talking about at the moment.
I see.
Well, thank you very much for joining us. And see you in the next episode.